Alright class, now the next topic that we're going to talk about is gases. Now why do we have to care about gases? We have to care about gases because we are surrounded by gases. Right now you are surrounded by hydrogen gas, H2, oxygen gas, O2, nitrogen gas, N2, carbon monoxide, CO, carbon dioxide, CO2. So you are surrounded by gases. So we need to learn about these gases that you inhale and you exhale on a daily basis. Now, before we talk about gases, the first thing we need to talk about kinetic molecular theory of gases. And I'm going to summarize this for you. I'm going to give you a very brief summary of what is a kinetic molecular theory of gases. It basically helps us. This theory is going to help us understand the gas behavior. It's going to help us understand why gases behave the way they behave. Okay, now it has number one, has a few parts to it. Number one, basically what it says gas particles, they move randomly with high velocity. So what does that mean? That means the gas particles, they move random directions at very high speed. What does velocity mean? Velocity means high speed, right? Really fast, basically. Basically, gases are moving around randomly, different directions, really fast. That's what it means. So velocity just means speed, right? High velocity means is moving around really rapidly. Now, number two, there is almost no, actually let me put them almost there in there too. Almost no attraction. There is almost no attraction between gas particles. They're not attracted. They're far away from each other. So there's almost no attraction between them. They're far away from each other. There's almost no attraction between them. Next one. And next one, you probably learned this back in high school, or actually elementary school. Volume of the gas equals the volume of the container. Now, technically, gases have a very, very, very small volume. If you compress all the gases in the room, you're going to have a very, very small volume. But if you let go of those gases, it will spread around and it would fill up the entire room, right? So if I gather all the gases in this room right now and I compress it down, it has a very small volume. But if you let go, the gases have a tendency to spread around and fill up the entire room. So because of that, the volume of the gas equals the volume of the container, because it has a tendency to spread out and fill up the entire container. So far, so good. Okay. Nice job. Now, let's go to number 4. Now, number 4, what it says, gas particle constantly moving rapidly, right? So, gas particle, and we talked about this already. Gas particles, they're moving rapidly, right? They're moving rapidly. They're moving rapidly. Now, sometimes when you're moving rapidly, what happens is you will collide. Now, what happens if you're moving rapidly and then you collide? You're just going to go to a new direction. Okay? You're just going to go to a new direction. So gases are moving around. And this is harder to show without you seeing me. So gases are moving around. And as they're moving around, they're going to collide. Then they're going to hit the walls of the container. So gases are moving around and they're going to hit the walls of the container. And then what that happened, and they're just going to go to a new direction. Now, here's the thing. The more collision you have, the more pressure you are exerting. So let's go over this one more time. So the gases are moving rapidly, right? After moving rapidly, they are going to hit the walls of the container. As you keep hitting the walls of the container, you're exerting pressure. More collision, you're going to have a higher pressure. Okay, so far so good. All right, let's go over the last one. The last one is average kinetic energy. Average kinetic energy is proportional to temperature. I want to talk about this a little more. So average kinetic energy is proportional to temperature. Now check this out. If you raise the temperature, do you agree that gas particles are going to move faster? So you raise the temperature. Now most of the gases have more energy, right? When you raise the temperature, they get more energy. They can move around faster. Now if you're moving around faster, what that means is you are going to collide more. You're going to have more collision, right? You're going to have more collision. Now, if you have more collision, what does that mean? The pressure is also going to be higher, because more collision means you're exerting more pressure. Okay, so that's why at high temperature you have more pressure. And you've seen this, for example, in wintertime. Sometimes when you go to drive your car, you notice that you don't have as much air in your wheels. Why is that? Because again, you have lowered the temperature, gases are not moving as fast, less collision, less pressure. In summertime, you don't have that. Your tires are actually pretty nicely inflated, because again, more temperature, high temperature, you move faster, more collision, they exert more pressure. You have enough pressure in your tires. Okay, now you got this down. Let's talk about one more thing regarding to this. Average kinetic energy, okay? And this line over here means average. So average kinetic energy, we said, is proportional to temperature. So what that means is, this is important, kinetic energy is only temperature dependent. Kinetic energy is only temperature dependent. Now, in your physics classes, you know kinetic energy is half mv squared, right? Now, check this out. If mass goes down, velocity goes up. Or vice versa. If mass goes up, velocity goes down. That makes sense. The bigger, it's like human beings too. The bigger we are, we cannot run around faster. Kids are tiny and they can run around super fast. So, mass goes up, velocity goes down. Mass goes down, velocity goes up. But it would end up, one goes up, one goes down, so it would end up balancing each other out. Now, average kinetic energy depends on the temperature. Is the average kinetic energy is only temperature dependent. I need you to remember that. All right, so far so good. Now, let's do a practice problem. Here's our problem. Again, pause me, do this problem, and I'm going to go over it together. You have in the same container, you have O2, N2, and CO2. Which gas moves faster? What do you guys think? Remember what we talked about? Half mv squared, right? When you are a lighter atom, you can move faster. That makes sense, right? A lot of the gases are common sense. The lighter you are, you can move around faster. So, among all these atoms, you see all these ones? The gas that is lighter is N2. N2 has a lower molecular weight, so it's lighter, it can move faster. The lighter you are, you can move faster. Remember that. Okay. Now, which gas has a higher average kinetic energy? Now, what did we just say about average kinetic energy? Average kinetic energy only depends on what? It's only temperature dependent, right? Only temperature dependent. So if it's only temperature dependent, if we are in the same container, what does that mean? Same container means all of these gases have the same temperature. If you have the same temperature, you have the same average kinetic energy. So it would be all the same. Okay? Now, I want to say this one more time just to make sure everyone is on the same page. Average kinetic energy is proportional to the temperature. Yes? Now, average kinetic energy is half mv squared, right? So what does that mean? Is the mass goes down, the velocity goes up. The mass goes up, the velocity goes down. So the lighter you are, the faster you are going to move around. Okay? One goes up, one goes down. This remains constant. Now, the average kinetic energy depends on temperature. As long as you have the same temperature, they have the same average kinetic energy. So remember that. Same container, same temperature, same average kinetic energy. So far, so good? Okay, because this one goes up, one goes down, this remains constant, and then you have to look at the temperature to figure it out. All right, so far, so good. So now that we talked about this theory, and you kind of know why gases behave the way they do, the next thing we're going to talk about the properties of gases. We're going to talk about properties of gases. Now, the first property is volume. And volume, we usually use liters for the unit. And remember what we talked about. Volume of the gas equals the size of the container. Volume of the gas equals the size of the container. Don't forget that. And it has to be in liters. Okay. So gases has a volume. Now temperature matters. So these are the properties of gases. Volume matters. Temperature matters. Okay. Now what's the unit for temperature? Kelvin. This is a unit we haven't talked about before. Kelvin is a unit for temperature. Let's talk about this Kelvin for a second. Have you guys heard of absolute zero? Yeah? I totally miss teaching you guys in person. I can't hear you right now, but hopefully you're answering me a little bit. So absolute zero. What's absolute zero? What absolute zero is the coldest temperature possible. Is the coldest temperature possible. Coldest temperature possible is negative 273 degrees Celsius. They said, you know what? This is the coldest temperature possible. Negative 273 degrees Celsius. We're going to say that this is 0 Kelvin. Why did they do that? To avoid having negative value for temperature. To avoid having negative value for temperature, they said, okay, so we're going to take the coldest temperature possible and we're going to make it to be 0 Kelvin. Okay. Now, here's what I need you to remember. That if you, don't do that. If you have degrees Celsius, if you add 273.15 to be exact, you can convert it to Kelvin. And you need to know that. So far, so good. Okay. So volume, temperature. Next one. The amount matters. Moles. They're usually denoted by N. Moles matters. Volume matters. Temperature matters. Moles matters. The last one, you can probably guess. The last one is pressure. Now, we know that pressure matters. Okay. Now, we just talked about this 5 minutes ago. Gases are going to collide with the walls of the container. Every time they collide with the walls of the container, they are going to exert pressure, right? They're going to exert pressure. Because what pressure is basically force per area, right? Is force per area. You don't really have to know this equation. It's more physics. I don't care about that. But what I do want you to know is that pressure, when gases are colliding with things, they are going to exert pressure. Volume, temperature, moles, and pressure. These are the 4 properties of gases. Now, I want to talk about this pressure a little bit more. Do you guys listen, to a weather channel? You probably don't. I don't know, now that you're home, you might. So back in the days, before iPhone, before there was an app that you can just click on it and figure out what is the temperature and what's the weather like. When I was you guys, we have to watch the weather channel to see what is the temperature of our town and what the weather is going to look like. And it was so stupid because you have to sit there and then wait for your city to show up. So you guys have it easy. But if you ever decide to listen to the weather channel, they talk about atmospheric pressure. I want you to know what is atmospheric pressure. You know how we said right now in the room that you're sitting, there are a bunch of gas particles moving around, right? So the gas particles that are moving around, they keep hitting you over and over and over again. When the gas particles keep hitting you, they're exerting a pressure on you. And that is the atmospheric pressure. Okay? Now, how would you measure the atmospheric pressure? And the first lab of Chem 1A, which seems a long time ago, we went over this. So how would you figure out the atmospheric pressure? The first Chem 1A lab, one of the things you had to do, you had to go and find a barometer. That's what we use to measure atmospheric pressure, using a barometer. So far, so good? Okay. Now, before I keep going, because I want to actually show you how barometer works. Let me see. Do I want to show you first, or do I want to give you the units first? I want to give you the units first. I want to give you the units for pressure. So again, barometer is how you would measure atmospheric pressure. So the units for pressure is 1 atm. And 1 atm is 760 millimeters of mercury. 1 atm also equals 760 torr. And 1 atm equals 101,325 Pascal, which you probably have heard of, which also equal 101.325 kilopascal. Okay. So these are the units for pressure. Now, I want to go back to the barometer. We use barometer to figure out atmospheric pressure. Now, I want to show you how the barometer works. This is so as you can see, my drawing on the iPad and on the board are pretty much the same. They haven't changed much. Okay. I'm going to draw a barometer because I want you to understand this concept. This is one of the cool stuff in Chem 1A, to understand what is going on if you ever decide to listen to the weather channel. Okay. Now, what I have in here, I have mercury in here. Now, why the heck in the world am I using mercury when everyone knows mercury is bad for you? Yeah, we know mercury is bad for you, but we are using mercury. The reason we're using mercury because we don't have much option. Mercury is the only metal that is liquid at room temperature, so we gotta use mercury. So here's the mercury in here. Now remember what we talked about? We said gases are going to exert pressure, right? Gases are exerting pressure. As the gases are exerting pressure here, the height of this mercury changes. So if you exert more pressure, what do you think is going to happen? The height will go up. If they exert less pressure, the height will come down. So again, how much pressure they're exerting on this mercury, the height will change. You guys are good? I have gases going on here. The gases are going to exert pressure. The more pressure they exert, the more the volume is going to go up. The less pressure, the volume will come down. Now, what they are measuring is this height here. This is the height. And they measure it in millimeters. That's how a barometer works. Now, who was the guy who came up with this? Torricelli was the guy who came up with this. Okay. Now, this is really cool because, come back over here. We said 1 atm is 760 millimeters of mercury. What does millimeters of mercury mean? It means over here. This height is in millimeters, and this height is the height of the mercury. So when this height is 760 millimeters of mercury, that's when we have 1 atm. Pretty cool, huh? Now, we also said that the guy who came up with this is Torricelli, that I wanted to honor him. So 1 atm is also 760 torr to honor the guy who came up with this. So far, so good. Okay. Now, these two you have to know for your exam. Pascal, I don't really care too much about it. It's not a SI unit, but those I want you to know. So far, so good. All right. Now, last thing. So now that you know barometer, you know where the units come from, there's one equation for a barometer that you have to know. And we usually have a lab on this. I don't know if you're still going to have the lab, but you got to know this one. Density of mercury times height of the mercury equals density of a liquid times height of the liquid. When we use a barometer, this is the equation that we use. Now, this sign over here, that sign is density. Rho is density. Density of mercury is 13.6 grams per ml. That's the density of mercury. Now, if the liquid is water, what is the density of water? 1 gram per ml. Okay, so far so good. So definitely know this equation. Now let's do a practice problem with this equation. Now, before I give you a practice problem to do, the one more thing I wanted to talk about is that the height of the liquid and the height of the mercury has to be in millimeters, right? Everything is in millimeters of mercury. Because again, here, millimeters of mercury. This is the height. All right, here's a practice problem, okay? Pause me, do this problem. Now, we're talking about a barometer, right? We're talking about a barometer. You go, okay, we're talking about a barometer. If that's the case, I know what is the formula. Density of the barometer times height of the barometer, density of the liquid times height of the liquid. Hopefully you pause me and you did this problem on your own first. Now, the density of mercury is 13.6. I will give that information to you on exam. Now, here they constructed a barometer with an unknown liquid and has a height of 130 centimeter at an external pressure of 0.93 atm. Okay. Now, they're asking what's the density of this liquid. So I know what I'm trying to figure out is the density of this liquid. So I just saw the word barometer. I wrote this down. And I knew I need the density of mercury is given. And I need the density of the liquid. So you can even, like, before reading the problem, you can figure out most of it. Now, but read the problem, okay? So we got this. Now, what else do we have? The height of this liquid is 130 centimeter. I can plug it back in here, except the unit has to be millimeters, right? So that would be 1300 millimeters. So far, so good. Now, I have to have one more piece of information, which means I have to have the height of the mercury. The height of the mercury would be the same thing as external pressure, right? Because remember, the external pressure that is exerting on the mercury will determine the height of the mercury. We just talked about that. Okay, except that is not given in a right unit. The unit they give us right now is ATM. What do I need to do? I don't need ATM. I need millimeters of mercury to plug it in. So 0.93 ATM. Okay. Now 1 ATM is 760 millimeters of mercury. So the ATM cancels out. I end up with 706.8 millimeters of mercury. Again, remember this. The external pressure is the same thing as the millimeters of mercury, right? You exert pressure. This height, which is the height of the mercury, millimeters of mercury, is going to change. That's how that number comes. Now, I'm going to come over here. I'm going to plug back in 706.8. Everything has to be millimeters. So if I do that, what I end up getting for X, my X is going to be 7.39 grams per ml. That's a bad ml. Grams per ml. So far, so good? Okay. And again, and I'm going to do one more thing. Again, you probably know how to do this, but I don't want to take any chances. You can ask any question. 130 centimeter. Remember, 1 centimeter is 10 millimeters. So the centimeter can cancel that. This is how I end up with 1,300 millimeters. Okay. Now, let's do another fun problem. This one actually is fun. Before I stop this lecture. Ready for next problem? Let's do it. Oh boy, it requires me drawing things. Here is a mountain. So we have a mountain right here. And this is the sea. Maybe I'm getting a little better at drawing. So right here, I am at the sea level. Okay, here's a question. And I want you to pause me and to talk it out with yourself. If you have someone in your room right now, talk it out. When you go at the sea level, the pressure is 1 atm. When you go higher up, when you go hiking, what's going to happen to the pressure? More than 1 atm or less? When you go below the sea, what happens to the pressure? More than 1 atm or less? Okay. Now remember, when you go hiking, when you get to the top, you have a hard time breathing, right? Have you ever thought about why that is? You're probably thinking about it, and you know the answer. Because when you go up higher, there are not as many gases. You're having a hard time breathing. There's not as much oxygen and hydrogen gases in air. So if you have less gases, that means less gases are colliding with you. That means you have less pressure. Less gases, less pressure. So that's why the atmospheric pressure is going to be less than 1 atm. You go higher up, less gases. That's why you have a hard time breathing. And then less gases are exerting on you. So you have less pressure. Now on the opposite, when you go swimming, there's a lot of pressure on you. There's a lot of gases dissolved in water. There are a lot of gases dissolved in water. So the pressure below the sea is actually more than 1 atm. A lot of pressure are getting exerted on you. Okay, that was like a fun little practice problem. Nice job. I will talk to you guys next time to continue with gases.